Hello and welcome back to the alphabet of astronomy. So today is brought to you by the letter E, and E is for expansion. The expansion of the universe, to be exact. So to understand the expansion of the universe, we need to go back to the early 20th century. Now back at this time, they actually didn't know if the Milky Way was the entire universe or not. So they could see these things in the night sky that definitely weren't stars, and they called them nebulae. And they didn't know if these things were inside the Milky Way galaxy or not. So then this astronomer Slipher had the idea to measure the relative velocities of these nebulae and use those relative velocities to help localize the sun's position within the Milky Way. And basically, what they expected was that the nebulae would have kind of random velocities. But that's not what he found at all. He quickly realized that almost all of the nebulae were redshifted, that is, that they were moving away from us. So to measure the relative velocities, they were using the Doppler effect. So basically, if either the source or receiver is moving relative to the other one, then the rest wavelength of a given emission or absorption is shifted, either red, that is to longer wavelengths, or blue, that is to shorter wavelengths. And so by looking for certain lines that they knew the rest wavelength of, they can determine the relative velocity between the nebulae and ourselves. So Slipher found that almost all of the nebulae were redshifted, they were almost all moving away from us. Andromeda was a big exception. It was blue shifted, that is, moving towards us. But almost all the other ones were moving away from us. So that was pretty puzzling, because that wasn't what they expected. Well then, Edwin Hubble came along and he started using these things called Cepheid stars, which we've talked about before, to measure distances to these nebulae, and he discovered that these nebulae were actually not inside the Milky Way at all, and they were other galaxies, just like the Milky Way. So Hubble measured the distances to 18 of these nebulae using Cepheids, and then compared that to their redshifted velocity, and he discovered what we now call Hubble's Law, which is that the recessional velocity increased the farther away that a galaxy was. And he had this very famous figure, which basically shows this linear relation. So Hubble's law is that V equals h naught d, where V is the recessional velocity, h naught is what we call the Hubble constant, and d is the distance to the galaxy. So this was published in 1929. And one really exciting thing about Hubble's law is that if we know h naught, that is the Hubble constant, then by measuring just the redshift of a galaxy, then we know how far away it is, which is really great for things that are too far away for us to be able to use things like Cepheids to determine their distance. And it really is an important part of what we call the cosmic distance ladder. And while all of this was going on with the observers, the theorists were actually also postulating possible expansion of the universe. For example, de Sitter published using Einstein's equations a model of an expanding universe in 1917. So both observationally and theoretically, we were kind of coming to this understanding that one, not only was the Milky Way not the entire universe, but that there were other galaxies just like the Milky Way and that they were expanding away from us. So wait, how does a recessional velocity equate expanding? Basically, the expansion of the universe causes this recessional velocity. Now, when we say recessional velocity, we're talking about the movement away from us due to the expansion of the universe. Each galaxy also has its own peculiar velocity, what we call the peculiar velocity. So the recessional velocity is not actually a velocity through space. It is space itself expanding and kind of carrying the galaxy along with it. And for this reason, it's not subject to the speed of light, speed limit. It can be anything, and it's not a physical velocity. It is a recessional velocity. Peculiar velocity, on the other hand, is the kind of velocity relative to space. So if you thought about the galaxies as like, seaweed floating on the ocean, the recessional velocity would be kind of the ocean currents and waves carrying the seaweed around, but the seaweed might still have its own motion relative to the water. Okay, so maybe you can kind of visualize how an expanding universe is kind of carrying all of the galaxies away from us, and that would explain why this recessional velocity equates with expansion. But what you might be picturing is, the Earth or the Milky Way at the center of some universe that's expanding outward away from the Milky Way. But the Milky Way isn't at the center of the universe. That would be very egocentric to think that, right? And so what's actually interesting about the expansion of the universe is that every observer sees all of the other galaxies receding away from them in the same manner because the entire universe is expanding. So a common analogy that's used to kind of help visualize this is a balloon. So imagine you have several galaxies that are not gravitationally bound to each other, located on the surface of this balloon. So this universe is a 2D universe, unlike ours. So this is just an analogy. But in this 2D universe, it's on the surface of the balloon, right? So they don't have any concept of off the balloon or inside the balloon. They're just looking at these two dimensions along the balloon. So hopefully what you see is as this balloon is expanding, all of the dots are separating away from each other. And none of them is in the middle. The entire thing is separating and expanding. What's also important to note about this is that the balloon isn't expanding into anything. Well, okay, it's expanding into 3D space, but like I said, we're considering just the surface of the balloon. So these little dots, these are flat people living on the surface of this balloon. And to them, the entire balloon is getting bigger, so their universe is expanding and getting larger, but it's not expanding into anything. It's just that the dimensions are getting bigger. So that's similar to what's happening in our universe. Now, obviously, this is not an exact analogy because we don't live in a 2D flat universe, but hopefully it helps you visualize it a little bit. There's also something called the raisin bread analogy, where if you have a loaf of bread that has raisins in it, as that bread bakes and kind of expands, all of the raisins are going to see all of the other raisins expanding away. Even if they're at the edge of the pan, the center of the pan, anywhere within the pan, they're going to be seeing the same thing. So this is what's happening in the universe. We are looking out in the universe and we're seeing all of these galaxies going away from us, basically, and the farther away you are from us, the faster they're going away. Now, if you remember earlier, I mentioned that Andromeda is not red-shifted at all. Andromeda is blue-shifted. So I just said that all the galaxies are expanding away from us, so why is Andromeda coming towards us? Well, that's because the expansion of the universe, while the expansion of the universe is happening everywhere, gravitationally bound objects aren't expanding. They're still gravitationally bound. And so we are gravitationally bound to Andromeda. It's actually coming towards us, and we're moving towards it, so relative velocity speaking, and we're going to merge with it in about 4.5 billion years. And this isn't because the expansion isn't happening, it's just because gravity is dominating at this scale. Another way to think about that is, for example, different forces, right, have different ranges at which they're kind of the dominant effect. So for example, if you think about two protons, they're both positively charged, so they should repel each other, right? The electromagnetic force causes them to repel each other. But nuclei are made of protons, and so there has to be some way to have protons next to each other, even though the force of electromagnetism is trying to repel them. And that's called the strong nuclear force. And basically what happens is as the protons get close enough together, the strong nuclear force becomes the dominant effect, and it's an attractive effect, and so it draws the protons together, and it kind of overwhelms the electromagnetic force which is trying to repel them. So in the same way, the entire universe is expanding, but some things are close enough together that gravity is the dominant force, and gravity is an attractive force, and it's holding us together. Hopefully that makes a little bit of sense. But so the distance between, the atoms of your body or whatever is not expanding. The distance between us and Andromeda is not expanding. But on cosmological scales of gravitationally unbound structures, the universe is expanding. So we talked about Hubble's law, and I said that it's really exciting. If we know h naught, we can use it to measure distances. So the question is, do we know h naught? And that's a very interesting question. So when Hubble first proposed this law, his very first value of h naught was 500 kilometers per second per megaparsec. So that's the typical unit that we use for h naught, kilometers per second per megaparsec. So that basically means for every megaparsec, or every million parsecs that you move away from us, the recessional velocity increases by a certain speed, which is in kilometers per second. Now, kilometers and megaparsecs are both distances, so you could calculate an equivalent that would just be a per second value, but the number we usually like to give, because physically it makes more sense, is in kilometers per second per megaparsec. So Hubble initially proposed 500 kilometers per second per megaparsec, although this was pretty drastically wrong. he was using some uncalibrated Cepheids. There were turned out to be two different populations, etc., etc., etc. Anyway, over time, we kind of converged on the fact that the Hubble constant was somewhere between 50 and 100 kilometers per second per megaparsec. And so you can see here the measurements kind of throughout the 20th century, really kind of getting more precise, getting more accurate, converging in on this value. And for a long time, we really couldn't do any better than that, about a factor of 2 in precision on how well we knew H0. But as astronomy continues to advance and we get better and better observations and instruments and theories, we can do a lot better. And so there are two main ways that we measure the Hubble constant. So the first is based off of what we call the local universe. And now local in, we're talking local in cosmological terms, so definitely not local, just down the corner. Because remember, we have to look far enough away that we're looking at gravitationally unbound to us objects. But we call it local because they're close enough that we can measure the distances and the velocities to them directly. So either using Cepheids, or we can use Cepheids to calibrate other standard candles like type 1a supernovae. And so basically we use these sorts of distance measurements, velocity measurements, and we can combine them. And this is what Hubble did, right? So basically this is just a refinement of Hubble's technique. And this gives us a value for H0 that's around 73 kilometers per second per megaparsec. In contrast, we also have a way of measuring it that's called the early universe measurement. So basically, we can look at the leftover radiation basically from the Big Bang. It's called the cosmic microwave background, and it is all around us. And it basically tells us about the very, very early universe, which is why this is called the early universe method. And so then using the models that we have kind of created for our cosmology of our universe, we can infer a present day value for H0. So H0 actually, it's called the Hubble constant, but it's not actually constant, but using this method, we can kind of convert it into an equivalent value to the present day Hubble constant. And this gives us a value of about 68 kilometers per second per megaparsec. Okay, 68 and 73, you might be thinking, okay, close enough. No. We've gotten good enough at doing both of these things that both of these numbers are actually known precisely enough that they are in significant tension. They are significantly different. And when scientists say significant, they mean significant in a statistical sense, right? So statistically, we do not think that these numbers agree. Of course, it's possible that one or the other method is underestimating its uncertainty, and if there was a larger uncertainty, then they might not actually be in disagreement. But it's pretty settled at this point, I think. I think we're pretty confident in both of these measurements, and so this is a real difference, and this is what's called the Hubble tension. There are some kind of other methods that are being developed that could be used to kind of come down on one side or the other. For example, gravitational waves are really exciting by kind of providing this alternate independent measurement using standard sirens instead of standard candles. However, we just don't have enough data yet to really actually know to actually measure this precise enough to weigh in on these values. For example, using gravitational waves, the value that they have gotten for the Hubble constant is consistent with both of these values. So you can see here kind of the modern day H0 measurements. So in black, we see the ones that are done using various forms of the distance ladder, so that would be the local universe method. And in red, you can see the ones that are based off of our early universe measurements, and then our cosmological model, which we call lambda-CDM. And then the blue are some of these independent measurements. The blue are not as precise as the black and red, and you can see that the black and red don't totally agree. So if you're hoping that now is when I tell you what the solution to the Hubble tension is, think again. So resolving the Hubble tension is a very active area of research with a lot of very smart people working on it. I think there's a kind of a growing consensus that this Hubble tension indicates something that we don't understand about the universe. So it's probably not an issue with our methods at this point. We think that it is an issue with a lack of understanding of the physics and the astrophysics involved, which represents a really exciting opportunity because that means that there's more to learn. And I, for one, think that's really awesome, and I cannot wait to see what the cosmologists and the astronomers come up with in the future years to resolve this Hubble tension and explain our universe. So there you have it. The universe around us is expanding as long as it's not gravitationally bound to us. And I hope you learned a little bit about the history and current state of the field of understanding the expansion of the universe. The expansion is also accelerating, but we didn't even get into that today. We're just talking about the good old expansion. So thanks for tuning in, and I hope I'll see you for the letter F. All right. See you again soon. Bye.